Hey guys, today we're going to be talking about topic 5 of IB/HL Computer Science, Abstract Data Structures. Our focus today is going to be recursive thinking, and we're going to cover the first 3 points under topic 5.1, which are all about identifying, understanding, and tracing recursive solutions. So to start, what is recursion? Recursion is a programming technique where a function calls itself in order to solve a smaller instance of the same problem. The idea is that we keep breaking a larger problem into smaller, simpler problems until we reach a case that's so simple that it can be solved directly. That's called the base case. Every recursive algorithm has 2 parts, the base case and the recursive case. The base case stops the recursion, and the recursive case reduces the problem step by step to eventually reach the base case. A good way to picture this is to imagine Russian nesting dolls. Each doll contains a smaller doll, and you keep opening them until you reach the tiniest one. That's your base case. Recursion essentially works in the same way in code. Now, where do we use recursion? You want to look for problems where the solution naturally involves solving smaller subproblems of the same kind. A classic example is calculating a factorial. If you remember from math, factorial of n is defined as n times factorial of n minus 1. That's a recursive definition. The function literally refers to itself. That makes it the perfect candidate for recursion. Another real-world example is navigating a file system on your computer. Imagine trying to calculate the total size of a folder, but inside that folder you have more folders, and inside those are more folders. To calculate the size of the entire thing, you'd recursively call a function that calculates the size of one folder, and within that function, call it itself again for every subfolder inside. The last example is solving a maze. Let's say you can move in 4 different directions and you want to find a path to the goal. At every position, you're going in each direction recursively until one of the paths leads to the end. The beauty of recursion here is that each smaller step is still the same type of problem. You're just trying to find the path from a new position. Now we're going to look at an example of recursion. Suppose we're asked to find the sum of all values in a list of integers. The instinctive approach might be to use a loop, but this can be solved recursively too. As we can see, this recursive pseudocode written on the left is the sum of integers that we input. So let's break it down. Our base case is if L is empty, then return 0. If it's not empty, we take the first element and add it to the result of calling the same function on the rest of the list, as we can see here, else return L index 0 plus sum list L 1. So it would look like sum list bracket 3, 5, 7. We're inputting an array because L is an array. This becomes 3 plus sum list 5, 7. Ooh, like that. And this becomes 5 plus sum list bracket 7. And sum list with nothing left inside of our brackets returns 0. Now when we work backwards, 7 plus 0 is 7, 7 plus 5 is 12, and 12 plus 3 is equal to 15. So when we put in sum list 3, 5, 7, we get 15 as our total sum. The point of this example is that recursion isn't just for mathematical problems. It can be used to solve many programming tasks where the structure of the problem can be broken into repetitive smaller chunks. Now we're going to look at tracing a recursive algorithm. This is something which will most commonly come up in paper 2 when you're asked to trace or follow the logic of recursive calls. Let's walk through another example using factorials. The pseudocode looks like this on the left. We have our base case, If n equals 0, then return 1, and our recursive case. So let's trace. Supposedly we did factorial 4. This would become 4 times factorial 3, and then this would become 3 times the factorial 2, become 2 times factorial 1, and this would be 1 times factorial 0. And factorial 0 returns 1. So then we can go back up the stack, and this would become 1 times 1 equals 1, 2 times 1 equals 2, 3 times 2 equals 6, and 4 times 6 equals 24. Therefore, our result is 24. So the final result is 24. Each time we make a function call, that call is paused and added to something called the call stack. It waits for the result of the next one before it can finish. Then the results bubble back up the stack until we get the final answer. This process is like a stack of plates. You can keep putting new ones on top as you go deeper into the recursion, and once you hit the base case, you can start removing them one by one, computing the result as you go, just like we did here. Now, before we finish, we're going to look at some common recursion mistakes. The most common issue is forgetting your base case, and if you do that, your function will keep calling itself forever, crashing your program. Another common mistake is not reducing the problem correctly in your recursive call. For example, forgetting to reduce n in n factorial means you'll never reach the base case. Lastly, don't try to use recursion for everything. For simple counting or looping problems, iteration is faster and easier. Always check that you clear your base case and each call moves towards it. Just to recap, recursion is about solving a problem by breaking it into smaller versions of the same problem. You always need a base case, and your recursive case must bring you closer to that base. We've seen how to identify problems suited for recursion, how to write recursive pseudocode, and how to trace recursive calls using the call stack. In IB exams, especially paper 2, you may be asked to trace recursive functions with lists, strings, or numbers. Practice following the logic step by step and writing out each function call in order. If you can visualize the stack, you can almost always solve it correctly. Thanks for watching.